it's my great pleasure to introduce Thieu, who will talk about rational solutions of first-order algebraic difference equations. And yeah, please go ahead.
Thank you. Thank you for the organizer of the seminar for giving me a chance to have a talk again in coaching seminar, differential equation, differential algebra. My last talk in coaching seminar was 5 years already. Today, I want to introduce to you my recent result about an algorithm for computing rational solution of first order algebraic difference equation, not differential equation. And I will separate it into 2 different parts. On the first part, I will introduce the main problem and some notation. And then the second part is devoted to the idea of the algorithm. The algorithm in the main theorem, in the main part, I will separate it into 2 smaller parts. The first part is call it associate difference equation. That means another difference equation which look easier, look simpler than original differential equation. And the second smaller part devoted to a completed algorithm for autonomous case. And in the end, I will explain why the idea doesn't work for non-autonomous case. Now let's go to the third part. In this talk, I assume that K to be the field of algebraic number, but the theory can work for any computable field of characteristic 0. And the difference operator I consider here is a shift operator. And the main object of the talk is first order algebraic ordinary difference equation that I write AO delta E for short. And a first order AO delta E is a difference equation of the form f x y y1 of 0, where f is a polynomial, and we can additionally assume that f is an irreducible polynomial. And a solution, of course, a solution means a function y equal to yx, so that when we substitute yx to the given AO delta E, we obtained identity. I will concentrate on rational solution only. That means a solution which is a rational function. And we also have the term rational general solution. Rational general solution have a formal definition which is quite long, and for short, we can think it at 1 parameter called rational solution. The detailed definition for rational general solution is not important here. So I should call it is just 1 parameter called rational solution. And among rational general solution, I focus on the one called strong rational general solution. And I will write SRC solution for short. They are solutions of the form Yx, and it may contain an unknown constant C, and Yx itself is a rational function on both variable x and constant C. That is strong rational general solution. Okay, the main problem is compute.
C here, sorry, I have a question. C here is a transcendental constant, or?
Yeah, C a transcendental constant.
Okay, thank you.
It is not in K. It is not in K. And the main problem is to compute a rational general solution of the first order AO delta E fx y1 equal to 0. I give here two examples. For example, the first one is an AO delta E of the first order and the second degree in y1. It looked not easy, and it had a rational general solution yx equal to c times x plus c squared. And this rational general solution is strong in the sense that the constancy appear rationally. And the second example, the other AO delta E of first order and second degree in y1, and it had one rational solution. I'm not sure whether this differential equation have other rational solution. No, this differential equation had no x. So when we reply x by x plus constant c, we will obtain a rational general solution. There are two examples about how a first order AO delta E look like. And the main problem is how to determine a rational general solution for them, if there is any. Before going to the main idea, let me say something about historical detail of this problem. Usually for difference equation, linear one are widely studied by several great mathematicians like Sergei Abramov, Bronstein, Peter Paul, Coep, Gotper, Van Hoy, or Michael Singer, and many other great mathematicians. And that is for linear difference equation. But for nonlinear difference equation, not so many of the result was presented. And for nonlinear algebraic O delta E can't provide a general setting for the problem of solving difference equation. The nonlinear case is much more complicated. For the autonomous first order, that means the AO delta E of the form f y y1 equals 0. First order arbitrary degree in y1 and no x. Thang and Gao presented a complete algorithm for computing a polynomial solution of this kind of AO delta E in 2008. At that time, they wasn't successful on finding rational solution because they cannot bound the degree of a rational solution. Long time later, me and Yi Yang, one of my Chinese colleagues, we revisit the methods of Thang and Gao, and we do a little more to obtain a bound for the degree of rational solution, and we completed the algorithm. That is for autonomous first order case. For non-autonomous, there's no completed algorithm at the moment. And my talk today will concentrate on this, on the blue result. Historical detail. Now we go to the idea of the algorithm. The idea of the algorithm can be separated into 3 different steps. Assume that we want to find a rational solution of the AO delta E fyy1 equals 0. That means autonomous one, no x appeared here. Then what we do is, first, we try to separate y and y1 in the sense that we will transform the difference equation to a new form in which y will be in one side and y1 will be in the other side. Separate one by one. And then after separate one by one, we will reduce that different that new form to a second order autonomous AO delta E with polynomial solution. So now we reduce from rational solution to polynomial solution, but the order will increase from first order to second order. And for polynomial solution of second order autonomous AO delta E, we can bound a degree. Now we go to the first steps, how to separate y and y1. We will define a new class of difference equation, call it associate difference equation. And we do it by using some technique from rational curve, parameterization of rational curve. Assume that we consider an AO delta E fx y1 equal to 0. And now in this step, I consider for non-autonomous case. We can consider autonomous case is a special case of the non-autonomous one when x disappears. And for AO delta E of this form, we define an associated algebraic curve C on the L5 line over the field kx bar. That means the field of algebraic function in X with coefficient in K. That means we consider y and y1 as the new variable, new two variable, and X to be the coefficient. Then we obtain an algebraic curve. And we prove that if f is irreducible, and if the AO delta E had a strong rational general solution, then we can conclude that f must be absolutely irreducible. That means that it is irreducible when we consider it at polynomial in y and z and coefficient in kx bar. Furthermore, the associated algebraic curve must be sub C not 0. So this is the first necessary condition for the AO delta E to have a strong rational general solution. That means f must be absolutely irreducible and the genus of the associated curve must be 0. The first necessary condition. Now we go a little more. When C of C not 0, then we can play parameterization on C. But we need some term from algebraic curve. Now we assume that F to be an arbitrary field of characteristic 0 and need not necessarily be algebraically closed. And we assume that E is an algebraic curve in the L5 plane over the algebraically closed of F. And E is defined by an irreducible polynomial C with coefficient in F. Then a rational parameterization of E. And sometimes I remove a rational and just say a parameterization of E. That is a birational map from the L5 line over F bar to E. And it is defined by a pair of rational function P1 and P2 with coefficient in F bar. Not every algebraic curve have a parameterization. Only C not 0 algebraic curve had a parameterization. And the algebraic curve of C0 0 will be called a rational curve. For each parameterization of E, we will have a look at the coefficient. The coefficient of P1 and P2 will be the element in some algebraic extension of the ground field F, and they will be called the coefficient of parameterization. And when people compute parameterization of rational curve, people try to compute a parameterization whose coefficient, like in a smallest field extension, as small as possible, and it leads us to a notation called it optimal parameterization. A parameterization whose the field extended from F by its coefficient is as small as possible. It calls it an optimal parameterization. Every C0 0 algebraic curve admits some optimal parameterization. And in our problem, the ground field F will be the field of rational function Kx, and we need a theorem that they proved it 3 years ago. Assume that E is a rational curve over Kx. That means E defined by a bivariate polynomial with coefficient or rational function in Kx, and assume that P is an optimal parameterization of E. Usually, the coefficient of P will lie in an algebraic extension of Kx, but in this case, we prove that the coefficient of P must lie in Kx itself. This theorem is important because when we work with the optimal parameterization and we use optimal parameterization of an algebraic curve to transform to a new differential equation, then we want to guarantee that the ground field Kx must keep the same and no square root of x appear. If some square root of x appear, or if some algebraic extension of Kx appear, then we will come to a more complicated differential equation, and that we don't want to be happen. Now we go to the transformation of the given differential equation by using optimal parameterization. We do as follows. Let fx y1 equal 0 be the given AO delta E. And now we can assume that the corresponding curve is of C0 0. And we can assume that PT, with a pair of P1, P2, rational function in x and t, be an optimal parameterization of C. We can add this assumption because of the previous theorem. And we consider a new differential equation, established by using the optimal parameterization. P1xt now become P1x plus 1 and omega 1. And P2xt become P2x omega, where omega is a new unknown function, and omega 1 is the shift operator applied to omega. And you see, in this new differential equation, omega and omega 1 are separate. Then we claim that there is a one-to-one correspondence between the strong rational general solution of the given AO delta E and the strong rational general solution of equation 1. And if we know solution of one, then we can derive the solution of the other. In particular, if omega is a strong rational general solution of equation 1, then we can substitute omega to P1 to obtain the strong rational general solution of the given AO delta E. And the equation 1 is called associative differential equation of the given AO delta E. So now we reduce a general first order AO delta E to a new one in which the unknown function and the shift of the unknown function are separated. So it looks simpler. The problem now is try to solve this kind of differential equation. We tried for the general case when P1 and P2 are arbitrary, but we will fail. And we restrict ourselves to a simpler case where X doesn't appear. That means we consider only autonomous AO delta E. And we are set at autonomous one. But for non-autonomous, we still have no idea how to process. And now we go to autonomous case. So we restrict ourselves to a smaller class of differential equation called autonomous differential equation. That is Fyx and Yx plus 1 equals 0. Now I use Yx plus 1 instead of Y1 because there's some more polynomial appear with in this 1, 2, 1, 2. So I don't want them to be confused. Now let's consider the autonomous differential equation f Yx plus 1 equals 0, where f now is an irreducible polynomial in two variables. Call it equation 2. By using the technique of the previous section, we can derive a separable differential equation like this. We prove that if equation 2 had a rational solution, then it had a strong rational general solution, of course, by shipping X to X plus an arbitrary constancy. Furthermore, the associated differential equation will be performed P1 Yx plus 1 over Q1 Yx plus 1 equal to P2 Yx over Q2x for some non-zero polynomial P1, P2, Q1, P2, Q2. And they are polynomial in one variable. This proposition is just a particular case of the previous theorem when we try to derive general first order AO delta E. And the problem now is to find all rational solution of the equation number 3. That means the separable one. How to find rational solution of equation 3? We do as follow. This slide, roughly speaking, some initial steps to go from rational solution to polynomial solution. This step is quite technical and long, and some detail in this slide will be written in several pages in the paper. But I ignore the technical detail and just introduce the idea. Sorry. From equation 3, now we want to find rational solution y. Then we write y equal to a over b, where a and b are polynomial. And then we substitute to the equation tree here. We substitute to the equation tree. So we have a P1 of a over b, x plus 1 over Q1 of a over b, x plus 1, and so on. And then we clear the denominator to have the form like this one. That means separable one again. But on the left-hand side, it contains two unknown polynomial, ax plus 1, bx plus 1, and ax, bx. We can show that the denominator and the numerator of both sides, they are the GCD, the GCD of the numerator and the denominator of the fraction on both sides are equal to 1. So the numerator must be equal to a constant times the numerator, and the denominator must be equal to the same constancy times the denominator. And that constant can be determined by comparing the degree and the leading coefficient of both sides. And we prove that there are only finitely many choices for that constancy. And the constancy can be determined from the given polynomial f. And after we obtain system 4 now contains two unknown functions a and b. We can use elimination technique in differential algebra to eliminate one and keep the other. And then we obtain a single second order autonomous AO delta E for each of them. And in the end of the day, we come to the new problem. That assume that we have a polynomial Z which is homogeneous. And the problem now is to find all polynomial solutions of the second order differential equation like this. There are some detail that must be more clearer in this line. The first detail is how to determine the constant. The second detail is, do we sure that elimination technique always work here? Both of them have positive answer in the sense that yes, we can do that. But in this talk, we ignore it. Now we come to the new problem. Find polynomial solution of a second order autonomous differential equation. We are going to bound the degree of the polynomial solution of the equation number 5. How to bound the degree of the polynomial solution here? We do as follows. We need an operator that is similar to the differential operator. We need the operator delta determined by the formula delta yx equal to yx plus 1 minus 2x. And then we rewrite the given second order autonomous AO delta E at a new one using the operator delta rather than the shift operator. And Z tilde now is a polynomial in 3 variables again. And we can write it down explicitly. we are seeking for the possibility for the degree of a polynomial solution. The possibility of the degree of a polynomial solution can be only appeared in the information from the initial polynomial. The initial polynomial is defined as follows. With the polynomial z given before, we determine z tilde like this, and then we take a sum. We take a sum of ai times t to the i2 times t minus 1 to the i3, where the run through the index of z tilde, so that I2 plus 2I3 must be the smallest value possible. That means we among the index I of the coefficient of z tilde, we determine I2 plus 2I3, and we collect the index I in such a way that I2 plus 2I3 is small, and it comes initial polynomial of T. And then we prove that first, the initial polynomial is always non-zero. That's the first thing. And the second thing, if Yx is a polynomial solution of degree D of the given AO delta E, then the degree D must be the root of the initial polynomial. So now we can bound the degree of the polynomial solution by determining about for the integer root of the initial polynomial. Yeah. So in the end of the day, we have the bound for the degree of the polynomial solution of the last one. So we can use an ansatz to determine all polynomial solution of the last one, and then we return back to rational solution of the given one. I give an example to illustrate the methods, the idea. For example, this one. This is an AO delta E of first order and second degree in Y1. And it looks ugly. And we want to find rational solution of this AO delta E. First, we consider this AO delta E as an algebraic equation in two variable y and y1. And this algebraic equation will define an algebraic curve. We can determine the z-naught of this algebraic curve. If the z-naught is not zero, we can stop the algorithm immediately and say that there is no rational solution at all. But this situation is not. In this situation, the z-naught of the curve is zero. Then we go on. We determine an optimal parameterization of the curve. It looks like this. And then the optimal parameterization leads us to an associated differential equation in a separable form. And now we try to solve this, the new differential equation. We substitute omega equal to A over B to the new differential equation, clear the denominator, compare the degree and the leading coefficient of both sides. We obtain 4 constant C. And the 4 constant C come to the 4 different systems like this. That denominator equal to numerator equal to C times numerator, and denominator equal to C times denominator. And each of the four systems, we eliminate one unknown function to obtain a single AO delta E in the other unknown function. And then it come to a second order autonomous differential equation, 4 of them for A and 4 of them for B. And then we can derive a degree bound for polynomial solution with a at most 4. And from that, we can determine the solution. There's some comment that I want to tell you before I finish my talk. The first comment is that although we can determine a degree bound for the polynomial solution of the second order autonomous differential equation that we obtain it at the end of the day, but we cannot control how large the bound will be. It is not good because maybe the bound will be very large at more than necessary. So we want to find a uniform bound for the degree of a rational solution in terms of the given AO delta E. And maybe the uniform bound will give a better algorithm. At the moment, we have a bound, but we don't have a uniform bound. I know we have a uniform bound, but we don't have a formula for that bound. That's the first comment. The second comment, the idea should work for autonomous one. When we come to non-autonomous, we have no idea. For the non-autonomous one, we can derive the given first order AO delta E to a separable one. But from the separable one, we don't know how to go further. And that is for rational solution. Maybe after that, we can consider algebraic solution. And this finished my talk.
Okay, thank you very much. So I suggest we postpone bigger discussion for after the break. There was a quick question, which I'm sorry I missed in the chat. William was asking whether the equations in omega are still polynomial or not. So I think the answer is that they are rational, right? It's like P1 equals P2. They are this is a rational equation in omega and in Y.
You're talking about this one, right? Number one.
Yeah.
Yeah, it is still rational in omega. P1 and P2 are rational function.
Okay, good. Then yeah, maybe we can now move to the discussion and discuss more about details after that. Ronnie?
Any question are welcome. There are many steps in this work still open. Some of them will be the future work.
Maybe let me start. So if I remember correctly, the whole this idea of solving equations using rational parameterizations was first invented for the differential case, right? And so I wonder, like, how much of the technology for differential case works in difference case, and what are the key differences, and what are the key subtleties you encounter in difference case compared to what happens in the differential one?
Okay. The key difference between the differential case and the difference case is how complicated it is in solving the associated differential equation. For the differential case, when we reduce the given algebraic ordinary differential equation to the associated one, then the associated one looks simpler and it can be solved immediately. But the differential case is more complicated. they know algorithm to solve the associate difference equation. We have to establish a new algorithm for that, and the algorithm is more complicated than the difference one.
Ah, so what you are saying is basically like until the slides you are showing right now, until this slide, these two theories are kind of similar, but then differential case is getting solved immediately, and you proceed for like 10 more slides.
Yeah, for a differential
Okay,
case,
okay,
until
good,
we
good.
come to this slide, it is like 99% solved.
Okay.
But for differential case like this, until we come to this slide, it is likely like 20% solved only.
Yeah, that's impressive. That's impressive. Thank you. Other questions?
Related question.
Yeah.
I have a closely related question.
Mm-hmm.
You mentioned that for you, one of the big open problems is how to treat the non-autonomous case. What is the status here for the differential case? Is for differential equations now possible to deal with non-autonomous algebraic differential equations?
So you are asking about the differential case. How does it happen with the differential case for non-autonomous AODE, right?
Exactly, yes.
For differential case, the problem of finding strong rational general solution of general first order non-autonomous case are completely solved. No open question anymore for the differential case. Maybe the new open problem come when we change to other kind of solution like non-strong rational general solution. Then it will then it is a different situation. But still, in strong rational general solution, we had a complete algorithm for non-autonomous first order differential equation already.
Thank you.
How about increasing the order, but still remaining non-autonomous? I mean autonomous, because in differential case you can just simply increase one variable, and you can just make a non-autonomous become autonomous, but just adding a variable, right? For the can you do the same thing for here and then work on second order?
Are you talking about the differential or difference case or both?
No, the difference case. So suppose instead of x, y, y1, you have x, y, y1, y2. Then you might have some surface instead of corresponding surface instead of a curve. Is this viable?
If we increase the order to the second order.
Yeah. So I mean,
I'm not sure in that case. I'm not sure in that case how the associated differential equation look like. Maybe it comes to a systems of differential equation of separable form.
Oh, you mean how to do separation? Oh, okay. Right.
I have no idea for that case. I have no idea for that case. But from my point of view, from my experiment, I have a feeling that autonomous second order is difficult at first order non-autonomous.
Well, it should be, I suppose, right? I mean, because
they are in the same level of difficulty, because I know that from first order non-autonomous, by using some elimination technique, we can derive a second order autonomous one.
Yeah.
And in some case, we can convert it back.
Actually, about that elimination of A and B, in your maybe fourth equation, in the element A and B, how do you know that you can just do it by increasing to second order and maybe not third order?
Thank you. Very good question. Actually, what I tell here is very short, and it is like one section in my paper. In that section, I prove that why elimination technique success here, and why the second order appears only. I do as they follow. From system number 4, I increase the order one more to obtain 2 more differential equations of order 2. And then we have a 4 differential equations in ax plus 1, bx plus 1, ax, bx, and ax plus 2, bx plus 2. So 4 differential equations in 6 unknown function. And I use some technique from parameterization to prove that the intersection of the ideal generated by the 4 polynomial, when we intersect to ax plus 1, ax plus 2, and ax, we can always construct 1. That is a reason second order in every case.
So in that result, are you allowing the P1 tutor and Q1 tutor and P2 tutor, Q2 tutor to be arbitrary? Or it depends on how you actually got that.
There are some conditions for P1 tutor and P2 tutor. There's some condition for P1 tutor and P2 tutor. And the condition come from the condition of P1, P2, Q1, Q2 here. For example, degree of P1 over Q1 must be equal to degree of P2 over Q2. So it leads to the degree of P1 tutor over Q1 tutor must be equal to the degree of P2 tutor and Q2 tutor in A. And in addition, because we clear the denominator, P1 tutor must be homogeneous. And P2 tutor, Q1 tutor, Q2 tutor must be homogeneous too.
Okay.
They have some condition.
Are they irreducible also?
Are they irreducible?
I suppose they're at least relative prime. I mean, P1 tutor and Q1 tutor, relatively prime, I suppose. I mean, you should be able to reduce them.
In general, no. In general, they are not irreducible. But the numerator P1 tutor and Q2 tutor, they are co-prime.
They're co-prime.
And P2 tutor over Q2 tutor, they are co-prime.
That you can always do, right?
Yeah.
All right.
No.
How hard is it to find the constant C?
How hard for finding the constant C? Actually, I derived a particular algorithm for determining all possibility for C.
Right. The example you gave has 4.
Yeah. Right. I have a table, and in the table I list the leading coefficient, the degree of P1 tutor, the leading coefficient of P1 tutor.
You mean the initial
degree and the leading coefficient of the other thing, and then compare each other. It's not difficult. It's just long.
Okay.
Not difficult.
So why is it in the initial equation I1 doesn't appear?
I1.
I mean, you have the index I, right? Which is I1, I2, I3. And in defining the initial equation, I think you call it P, if I remember, you only required I2 plus 2I3 to be minimal. There's no requirement on I1. Why is that? Which is the power of X, I think. Could you scroll to that slide, please?
Are you talking about this line or the previous one?
No, the initial equation.
The next one, the next slide.
The next one.
It should be
The next one. This one?
Yeah.
Right, yes. Oh, G, you call it G. All right. No, the piece of GT. So so in piece of GT, I1 doesn't appear at all, right?
In PC of T, I1.
I sub 1 doesn't appear.
Yeah, I1 doesn't appear at
So
all.
why is that? Why is that? Why is the power of Y1, Y rather, the first variable in your YZW, why is that unimportant at all? After you change it, after you change the difference operator to capital delta.
Yeah, let me remember why one didn't appear here. When we derive the initial polynomial C here, what we do was we write yx at we only consider the leading term of yx, and then we substitute the leading term of yx to z tilde, and then we consider the leading term of the product, and we group the leading term of each product together to have this guy. And I remember in the term, someone appeared with I1 before, but it had the same, it had the same term for every monomial. So we can put it out of the sum.
Oh, okay.
And then make it disappear.
Oh.
That is what I remember. That means that there is a term with something like t to the I1 or something like that. But that term, that containing I1, is the same for every monomial here. So we put it out of the sum,
I see.
and then it doesn't affect the degree anymore.
And I know it's technical, but how do you figure out this? I mean, how does this form involving t and the t times t minus 1, and then also the I2 plus 2, I3 small as possible? How does these things come about? I mean, it looks like magic.
Yeah, it looked like meshes. Maybe let me open the paper in the right place. I have the paper here. Do you see the paper?
Yeah.
Yeah.
Polynomial solution of autonomous second order homogeneous LDE. We are in the right subsection. In this subsection, we consider following problem that add be a trivial right homogeneous polynomial for on monomial solution. Okay, go down. Z now be F and Z tilde now be F tilde. And here, the story related to your question come from here. No, we need to go down.
No, I thought we.
Here. It appears here. So, so this is how each monomial count when we substitute yx and delta yx and delta square yx to each monomial, and we catch only the leading term. We catch only the leading term, and we do computation in the leading term.
Okay.
And you see, after some step, the one containing I1 will be grouping together, and it becomes I1 plus I2 plus I3.
Right.
So I1 appeared in the sum I1 plus I2 plus I3. However, our polynomial are homogeneous. So this sum
It's only the same, right? Right.
will be the same.
Right. Okay. Thanks.
That's the first thing.
Yeah.
The second thing, why we have d times
The
d minus
difference
1.
operator.
This because the delta square, because of the delta square. The d appear because the delta, because of the delta operation.
Right.
And d times d minus 1 come because of the delta square operator.
Mhm.
Yeah.
Okay.
I have again a related question. This reminds me a lot how you do this of the Newton-Puiseux method. Can this indicial polynomial somehow be interpreted as polynomial coming from some Newton polyhedron?
Actually, this is Newton polygon methods.
Yeah, it is. Yeah.
This is not exactly Newton polygon, but it is like I follow the step by Newton polygon.
So it looks like that, at least in this portion, you can do more variables. I mean high order difference equation.
Yeah. Even non-autonomous.
Right.
Even non-autonomous. However, it may happen in the general case that the indicial polynomial will be equal to 0.
Will what?
I mean, the indicial polynomial.
Yeah, would have more terms.
In general case, the indicial polynomial may be equal to 0. In our case, we just restrict ourselves on autonomous first order, then the indicial polynomial is always non-zero.
Okay.
Then we can obtain a bound for the degree of polynomial solution.
So in other words, you're saying that the constant may not exist for high order. Is that correct?
Yeah.
Okay.
And maybe the constant will appear in
or actually could be arbitrary rather.
Yeah.
If the polynomial initial polynomial is 0 always, then any C would work.
I remember for the first order non-autonomous, it worked. But when we go to second order, it doesn't work anymore.
Okay. Is there any bound on the degree of this, the PG sub T, P sub GT, on the degree?
Could you say again?
Is there any bound on the degree of P sub GT, the initial equation, where you get a constant? How many constants can you bound? The number of constants?
The number of constant.
Well, roughly at least. Not counting repeated roots.
Are you talking about the degree of PG?
Yeah. The degree.
The degree of PG.
Oh, sorry, I was mixing up with the constant and the degree. Yeah.
I think the degree of PG is determined. It is equal to the smallest possible values of I2 plus 2I3. It is I2 plus 2I3.
Yeah. So PG of T has just one term?
No, they may have several terms.
I mean homogeneous rather. They're homogeneous.
Yeah.
P is homogeneous.
Yeah, they're homogeneous.
Okay.
The smallest possible value of I2 plus 2I3 is unit, but there may be several pair I2, I3 satisfy this condition.
Right. right? So they're homogeneous, right? Okay.
Yeah.
Oh, but can I2 and I3 be one of them be zero?
Can I2 and I3, one of them could be zero?
So it will not be homogeneous if that's the case, right? Or is it? Oh no, it's still homogeneous. It's still homogeneous. Sorry about that. Yeah, but they might be zero.
It may be maybe.
So I2 is even and or something like that. And
I think there's some case that either I2
I3
or I3 could be zero.
Yeah. Okay. But they're still homogeneous. That's the
They're
main
still homogeneous. They
Yes.
are always homogeneous.
Right. Okay. Thanks.
Thank you.
Okay, any other questions?
So,
Maybe let me.
Yeah, Michael?
okay, I would like to ask you some questions regarding the algorithm. Okay, in your work, you have worked on the field K. I think you denoted it by capital K. So now, suppose I'm asking about any you are working with difference equation here, but say given difference equation or a differential equation, there are finitely many say complex numbers. Can you incorporate those complex numbers probably say which are transcendental over Q and give an algorithm?
Are you talking about the ground field, changing the ground field from rational number to complex number?
Yeah, I'm just asking that while implementing the algorithm, say your difference equation or as such your differential equation or difference equation, say there are finitely many transcendental constants appearing in the equation itself. So then can you implement the algorithm?
Can I implement the algorithm? Yes, I can, for sure. I do like 100 example already. I have not had the completed code yet, but given arbitrary differential equation, I know how to go step by step. And it is implementable.
Okay. One more thing. Suppose you are now while finding your solution, you have a degree bound, and then you are while you are doing the symbolic computations. Now, suppose at some stage. I think it could be a very immature question also because I've just started working on this algorithms. So, say you you are doing symbolic computations. Does it polynomial multiplication and symbolic computation? It takes a longer time. So, do you have any other method for solving the system of equations you will obtain other than Grosvenor basis? I mean, it has exponential time complexity. That's why.
I have not estimated the complexity of this algorithm yet. However, from theoretical point of view, the complexity of this algorithm will be expensive because it contains one step, that computing optimal parameterization of a rational curve. And that step is expensive. I don't know how it should be in comparison with the the complexity of computing Grosvenor basis.
No.
But I have no idea because I have not estimated the complexity of this algorithm yet. I just have a feeling at the moment that the complexity will be expensive.
No, I'm asking. Say once you get the D, that is the degree bound for your polynomial solution or your rational solution, and then you try to then we do symbolic computations. So then I'm just asking that while doing those symbolic computations, so do we always have to use Grosvenor basis, or is there any other method for finding the indeterminates? I mean, the coefficients of the polynomial solution.
Sorry, for finding the coefficient of what?
Say once you obtain the degree bound, then using that degree bound, you try to.
Mhm.
Did you get my question?
Okay, okay. Are you asking after having the bound for the degree, how I find the solution, right?
Yeah. So
at the moment, there are two different methods to do it. The easy way is to make an ansatz with a known coefficient, make comparison between coefficient by coefficient, create a system of algebraic equation, and then solve it by either Grosvenor basis or triangular decomposition or some similar technique. But I don't do it that way because it's expensive. There is another way that when having the bound for the degree, I try to determine a formal power series solution until enough degree, and then I use an approximation to approximate that formal power series solution by a polynomial equation.
thank you very much.
But how do you know the initial conditions then? So how do you choose the initial conditions for power series solution expansion?
Actually, when you have degree bound, then there is a criteria to decide how large, how many first coefficient of the formal power series solution do you need to have. When you have the number of coefficient of the formal power series solution you want to have, then you can start from an initial point, that is a regular point on the algebraic curve, and then determine one by one the next coefficient until you reach enough number of coefficient of the formal power series.
Thank you. Yeah, that's nice. That's nice.
You're welcome.
Any other questions to the speaker?
Yeah, let me ask one
sure.
more question. So if you look at the perfect difference ideal generated by your original difference equation, in general, it need not be a prime ideal. So in general, you can have more than one component. Does that somehow come up in the algorithm? How is the algorithm dealing with this, with the case where you have several components? Or is this somehow excluded? Like you just assume there's one component?
Actually, in our algorithm, the number of components doesn't affect the correctness of the algorithm. We go in the way that the number of components in the prime decomposition is not important anymore.
Okay.
Maybe you have several different components. In a good case, one of the components may contain the rational general solution, but we don't care. In this idea, we don't care which component contain. We decide from do some transformation to the new differential equation, and then the new differential equation, and come to polynomial solution of the new differential equation, and then we bound the degree. So the number of component of the prime and the number of the prime component is not necessary anymore in this idea.
Yeah. So in general, there could be more than one strongly rational general solution, right?
Yeah, I agree with you. There may be more than one strongly general solution.
But your algorithm would find all of them.
All of them for autonomous case.
Okay. Yeah. Sure. Okay.
Yeah.
Okay. Any other questions? Well, then let's thank the speaker. Thank you very much for the talk and then for this nice discussion. So see everyone in a week. We will have a talk by Garrett Jones.